Design of strap footing assumptions. This is a special type of footing used for the two columns. The two columns are provided by two separate footings connected by a rigid beam called strap beam. Let me show you the figure. Okay. Such type of footings are usually used when the property line and the face of the column are same. Instead of going for an eccentric footing, it is better to go for a strap footing. Okay. This column has an individual footing. This column has again an individual footing. These two footings are connected with a rigid beam known as strap beam, and such footings are called strap footing, right? Okay, so let us move forward. The footing areas are proportional in such a way to keep the pressure under the two footings uniform and uniform and equal, and for the center of the combined footing area to coincide with the resultant of the two column loads. This is done to avoid differential settlement of the footings, right? Let me explain you to the figure. Okay, the footings, the area of the footing or the dimensions of the footing are so adjusted that the resultant passes through the CG of the footing so that we get an uniform upward soil pressure below the footing. Let me show you the figure. Okay, so you can see this figure, right? Okay, so this is a very important point which has to be satisfied in case of strap footing. Okay, you should have an uniform upper soil pressure, and plus the upper soil pressure below both the footing should be equal. Okay, so there is no differential settlement. Okay, this is very important. Okay, so moving forward to the next assumption. Okay, it is assumed that the strap beam is rigid and does not transfer any load by bearing on the soil at its bottom contact surface, right? So this strap beam does not transfer any load through bearing of soil. Okay, this beam only transfers moment from one footing to other footing, right? So this will see as we take an example, and your mind will get more clear. Okay. The strap beam should be adequately attached with both columns by the by the use of dowels, such that both footing and the strap beam acts as an one unit. Okay. The reinforcement detailing should be such that this whole unit act as a one unit. Okay. Okay. Main tensile reinforcement shall be provided at the top of the strap beam between the columns, and the main tensile reinforcement for projected cantilever shall be provided at the bottom, right? Okay, we can visualize that the beam between this column, the beam between these two column, in this case, the tension will be at top. Okay, so the main reinforcement will be at top. This is a cantilever projection. Okay, in this case, the tension will be at bottom. So for this cantilever, the main steel will be at bottom, right? So this is very important. This we will see the deflection diagram as we solve the example. Check for deflection can be avoided as the footing are beneath the ground and are not visible. Check for crack width is must. In severe condition, the crack width should not be greater than 0.2 mm. In moderate condition, the crack width should not be in severe condition, the crack width should not be greater than 0.2 mm. In moderate condition, the crack width should not be greater than 0.3 mm. Our footing, which the design example which we are going to solve, falls in a moderate condition. So we will check the crack width for this condition. Okay. So let us start with an example. Okay. Design a strap footing for following factor loads and moments. Partial load factor to be taken is 1.5. Use M25 grade concrete and Fe415 steel. The effective cover to be taken is equal to 75 mm, and SBC is 200 kilonewton per mm square. Okay. So P1 is the factor load acting on C1. P2 is the factor load acting on C2. mx1 is the vector moment acting on C1, mx2 is the vector moment acting on C2, my1 is the vector moment acting on C1, my2 is the vector moment acting on C2. Okay, so is the this is a combination of loads which we have to design a strap footing, right? Okay. So the first step is that we have to first find the distance of resultant. Okay, so we have to find the location of the resultant, and after finding the location of resultant, then we have to set our size of footing such that the CG of the footing and the resultant coincides with each other, right? So first we will find the location of the resultant force, right? So find the distance of resultant force from the CG of the column C2, okay, along the length of the footing, okay. So along the length of the footing, okay. So this is the CG of C2, okay. From here we want to find the resultant along the length of the footing. So simple, just take the moments about this CG. This is P1, P1 this is 6 meters. So P1 into 6 meters, this is anti-clockwise, P1 into 6. This is clockwise, mx1, so this is minus. Mx2 is anti-clockwise, so it is plus, right? This divided by r, that is equal to your distance of resultant from the CG of column C2, and that is equal to 2.6 meters. Okay, so we have our resultant force at a distance. This is CG of column C2, and we can see the resultant, that is P1 plus P2, right? P1 is 750, P2 is 1000. These are factor loads. Okay, so R is 1750 kilonewton, which falls at a distance 2.6 meters from the CG of column C2, right? Now we have to find the eccentricity in this direction, right? Simple. We can, in our case, the CG of C1 and CG of C2 are in one line. So this is the line connecting the CG of C1 and C2, right? So this forces are on CG, okay? So this will be nullified because this will not produce any moment, because as they are on the line of CG connecting C1 and C2. We have two moments, mx1 and m by 1 and m by 2. Okay, so m by 1 plus m by 2, these two moments are equal and opposite in nature. Okay, we can see over here in the, this is plus 50, this is minus 50, right? So this turns out to be 0, right? That means the resultant force is acting on this line itself, right? Which is shown over here, right? It is acting on the line connecting the CG of C1 and C2, okay? So there is no eccentricity in this direction, okay? You can also find the distance of a resultant by taking the face of column in consideration. In that case, the moment due to this P1 force will be P1 into 0.25. Okay, the depth of the column is 500 mm, so half of it will be 0.25 meters. So P1 into 0.25, okay, P2 into 0.25, okay, and this is clockwise, this is anti-clockwise, so that is minus, this is again clockwise, so that is plus, okay, and divided by r, that is P1 plus P2, okay, that is equal to 0.25, right? So from the face of column, when you go to a distance 0.25 behind, then automatically you again come to the line passing through the CG of C1 and C2, okay. So this is how also you can find your y and come to a conclusion that the resultant falls on the line passing to the CG of C1 and C2. So eccentricity in this direction is 0, right? So that is what is shown over here, okay? Fine. So now as we have found the location of resultant force, now the next step is, now we have to assume the dimensions of our footing in such a way that the CG of the footing falls below this R, right? Okay. So let us assume assumption of footing area, right? Service load are factor load divided by 1.5. 1.5 is load factor, okay, partial load factor. So this is your service load 1167. Now weight of footing and backfill we are considering is 15%. 15% of this, that is equal to 175. Now minimum total area of footing required is this plus this divided by SBC. This is equal to 6.71 meters square. If we take the square root of this, then we can take B is equal to 2.59. Okay, but I am not going to take 2.59. I am going to apply another logic. Okay, what logic I am going to apply is, okay, the factor load on column C2 is 1000 kilonewton. Okay, so unfactored load on C2 will be 1000 divided by 1.5, that is 667 kilonewton, and considering 10% load of this as the weight of the footing and the backfill, that is equal to 67. So this plus this divided by SBC, this is equal to 1.91, and square root of this, right? This is equal to 1.91 meters. So I will assume the width be as 2 meters and not 2.59 meters. Okay, I'm going to assume the width of footing as 2 meters, and I'm going to keep the width of this footing and this footing to be the same. Okay, and as we know that for a square column, the footing is this, the size of the footing is also kept square, right? If it is a rectangular column, then the footing is kept to be rectangular. But this is a square column, so we will keep the footing square. So we'll take B equal to L2, and that is how I have assumed L2 is equal to 2 meters, right? Now, so now we know B, we know L2, we know B. Now we have to just find L1. Okay, now we have to select L1 in such a way that the CG of this footing will coincide with the resultant R. Okay, that's what I've explained over here, right? So now let us move forward. This is the footing in plan. Okay, this dimension we know 2 meters, 2 meters. This we know 2 meters. L1 is to be found. Okay, and this is the footing for column C1. This is the footing for column C2. The total out to out distance is 7.25 meters, and the distance between the CG of two footings is 6.25 minus L1 by 2. Okay, so what will we do? We will simply take the moment of area of this footing about the CG of this footing, right? So simple, 2 into 1 into this distance, which is written over here, right, has to be equal to x bar. X bar, we know that the CG should be 2, CG should be at a distance 2.6 from the CG of this column, right? CG of this footing you can say, or CG of this column you can say, both are same. Okay, so this is known to us. So x bar is known to us, that is 2.6 into area of this footing plus area of this footing, right? So that is what I have written over here. From that we get this, and we get a quadratic equation from this. Solving this quadratic equation, we get L1 is equal to 1.94. We will round it off, assuming L1 is equal to 1.95 meters. This is a very small adjustment. Okay, this will not affect the results much. Okay, the upper soil distribution below the footing will remain uniform. Okay, so this is how now we have the dimension of the two footings. This is 2 meter by 2 meter. This is 2 meter by 1.95 meters, right? Now we have to assume the dimensions for the strap beam, right? Now our column is 500 by 500. I am going to keep 50 mm projections on both the side. Okay, so 500 plus 50 plus 50, that is equal to 600. So I will keep the width of the beam as 600 mm. Okay, so I am taking width of beam is equal to 600 mm. Total length of the strap beam is 7.25 meters. So I will assume the depth of the strap beam D equal to 750 mm, because I have to keep the strap beam rigid. Okay, fine. So now we have given all the dimensions. Okay, whether it is footing or it is strap beam, right? So we have all the dimensions. Okay, Now the next step is to check whether the upward soil pressure below the footing is within the allowable limit. Okay, so the upward pressure should be less than SBC, definitely. Okay, so find the upward soil pressure below the footing. So that is equal to service load is factor load divided by 1.5, that is 1167 kilonewton. Weight of 15 footing we are, plus backfill we are taking as 15% of the service load, that is 175. So this plus this divided by area of this footing plus area of this footing, so that is area of, this is the area of this footing, this is the area of this footing, right? So that is equal to 169.87, which is less than 200. That is our soil bearing capacity. So the size of the footing is okay. All right. Okay. Now the next step is we have to find the net factored upward soil pressure for which the footing has to be designed. Okay. So the net factored upward soil pressure will be Q is equal to R divided by area. This area is area of this plus area of this. This is the area of this footing. This is the area of this footing. This is your factor load. So this divided by this is equal to 221.52 kilonewton per meter square. Okay. So for this net upward soil pressure, we have to design the footing, right? So this is what is shown over here. Q is equal to 221.52 kilonewton per meter square. So the first step now we'll do the design of this cantilever slab, right? This is a part of a footing. Okay, we know in case of footing we do not provide shear reinforcement. Okay, so shear will be the governing factor which will decide the depth of the footing. In this case, you need not do the check for punching shear. You can do only the check for one way shear because we have a strap beam along through and through. So check for punching shear is not needed. Okay, right. So let us now assume the depth of this footing. Okay, fine. Design a footing for column C1. Okay, in case of design of footing, we are going to take a 1 meter design strip. Okay, as the pressure below this footing and below this footing is the same, so whatever design we get over here will be applicable over here also. Okay, fine. So now we will assume a depth, or we will find the depth of the cantilever slab using one way shear criteria. We know that the critical section for one way shear criteria is at a section D from the face of the support. Over here it is beam, so we have to take our critical section at a distance D from the face of the beam. Okay, so this is the one way shear section at a distance D from the beam. Okay, so we know that this area, okay, due to this upward soil pressure will produce a shear force V, which will be equal to V is equal to Q into this area. Okay, this area is L1 into 0.7 minus T, right? So this is how we get this equation, right? Now another equation we get is V allowable, right? The shear the shear force at this section which is allowable, that is due to the permissible shear stress in concrete. Okay, that is equal to tau c into L1 into D. Okay, tau c into L1 into D. Okay, we know as I told just now that in case of footings we don't provide shear reinforcement, so all the shear has to be taken by the concrete. That is why our actual shear should be less than allowable shear, right? We are assuming that these two are equal and equating these two. Okay, we find a effective depth D equal to 266.65 mm. Okay, now as a structural designer you can round it off this to 300 mm. Okay, but I am going to take effective depth D as 350, okay, because I always I always like to remain a little bit conservative in case of footings, right? So I am going to take effective depth D equal to 350 mm. Of course, it depends upon the designer. Some designer may take this as 300 mm, okay, but I am going to continue with effective depth D as 350 mm, okay. And so overall depth D is equal to effective depth plus effective cover. Given to us is effective cover is 75 mm, effective depth we are taking as 350 mm. So this is equal to this is equal to 425 mm, okay, fine. So we can see over here, right? So this total overall depth now is taken as 425 mm as assumed over here, right? Okay, now after this assuming the overall depth, now the next step is we have to check whether the depth assumed by us is adequate or not. That is why we have to do the check for minimum depth required, right? For that we will have to find the moment first. So for finding the moment, design moment is found at the face of the support. Over here we have to take the critical section for finding the bending moment at the face of the beam, right? So this is 0.7 meters, okay. So this is your force Q. So this force V, this is upward pressure Q, sorry, it's a upward pressure Q, okay, 22 to 1.52 kN per meter square. This is upward pressure. So this V will be this pressure into this distance into this, okay. So this is the area. 0.7 into 1.95 is the area into this pressure will give you the force which will be acting at the CG of this footing, and that into this distance will give you the moment, that is 0.35 meters, right? So this is how we get the moment equal to 77.532, okay. And now we are very known with this formula for this is the formula for finding the minimum effective depth required for this moment, right? So this is found to be 149.9, which is less than 350. So we have provided more than required, so it's okay, and the section is under reinforced, okay, fine. So after doing this, now the next step is we have to find the tensile reinforcement required for this footing. Okay, this is the cantilever, right? So the mean steel will be in this direction, okay, and the distribution steel will be in this direction, right? Okay. So moment we have calculated, it is 77.532 kilometer meter. EST minimum is found to be 510. You can use this formula because it is a rectangular section, and that also singly under info section. So you can use this formula for finding the steel, and you get EST required as 634 mm square. As this required steel is greater than EST minimum, so we'll go with this, right? Okay, if this was less than this, then we will have to go with EST minimum, but our is greater than EST minimum, so we will go with this area, right? Now we have assumed due to shear criteria, okay, I just how did we get tau c over here? That is okay, that is I forgot to mention over here, okay. uh, over here we are assuming percentage of steel, tensile steel, as 0.25, for which the permissible shear stress of concrete tau c is 0.36 Newton per mm square for M25 grade concrete from table 19 of IS 456/2000, okay. So this is the assumption which we are making, and from this assumption we are getting tau c, and from this tau c we got our D effective D equal to 266.65, okay. So this was a very important assumption which I forgot to mention, and so I'm mentioning it now, okay. So we have assumed PT is equal to 0.25% from the one-way shear criteria, okay, and as according to that we assume to a depth, okay. Of course we are assuming depth greater than actually required, but still we will move on with this percentage of steel, Okay, so according to that assumption, when PT is 0.25%, then EST required is 875 mm square per meter. Okay, so we have to take greater of this two, this or this, right? This is greater, right? So we will go with this 875 mm square per 1 meter. So now we will be using 12 dia bar as main steel. Okay, and so the spacing can be found by this formula, and this is the area of 12 dia bar. The spacing is found to be 129.2 mm center to center, right? Okay, so we will provide 12 dia about 125 mm center to center. As according to code, this spacing, and the maximum spacing should not be greater than the lesser of these two, right? 3D or 3 times the D, that is 1050 or 300 mm. Our is 125 mm, which is less than this two, so it's okay, fine. Okay, right. So let me now show you this in the reinforcement detailing, that how do we provide this main steel in the cantilever slab, which is a part of the footing. Okay, so let me show you the figure that is for reinforcement detailing, which is at the bottom of the here, right? Okay, right. So this red dots are the main steel. These main steels are going to be in this direction, right? Okay, and this is distribution steel, right? So this is 12 mm about 125 mm. Same detail is provided for this footing also, so you can say 12 mm about 125 mm center to center, right? Now let us find the distribution steel, that this is the distribution straight line. This straight line is the distribution steel, right? Okay, important point. We have assumed the effective cover as 75 mm, which is shown over here, right? This is 75 mm, right? Okay. Now let us find the distribution steel required for the cantilever slab, which is part of the footing. Okay, simple. We have already found EST minimum. Okay, the EST minimum was found to be 510 mm square. Okay, so EST minimum is 510 mm square. We will be using 10 mm dia as distribution steel. Spacing can be found by this formula, okay, which is very well known to us. So from this we get the spacing of distribution steel, that is 10 mm dia equal to 153 mm center to center. Now this distance, this spacing should be lesser of this two. Okay, as according to code, it is 5D or 450 mm. Okay, 5D is 1750 mm, and this 450. Our is we will provide 10 mm dia about 150 mm center to center, which is lesser than this two, so that is fine. Okay, so let me again refer to the reinforcement detailing, where I will show you that how we have placed the distribution steel for the cantilever slab, which is part of the footing. Okay, and so let me show you that in the drawing. Okay, so this is the distribution steel, this straight line, right? You can see 10 mm about 150 mm center to center distribution steel. You can see this 10 mm about 150 mm center to center distribution steel, right? So this is how we do the design of the cantilever slab, which is part of the footing. Now after doing this, we will go for the design of the beam, right? Okay. Now beam we will be considering as a lying element. Okay, so the load on the beam should be a UDL, that is with a unit kilonewton per meter, but our soil pressure below the footing is in kilonewton per meter square, right? Okay, fine. You can see the upper soil pressure below the footing is in kilonewton per meter square, right? So this is C1, so this is C1. Okay, this is C2, this is C2. Okay, this is a small, this small distance is 0.25, and this is 1 meter, so 1 meter, right? Okay, so we have to convert this pressure into UDL. So this Q into 2 meters, that is equal to 443.04 kilonewton per meter. That is the UDL which we have to take on the uh, uh, beam, okay, which we are considering as a line element, okay. Fine. So from this we can see the deflection of beam will be like this, okay. So over here the tension will be at top, over here the tension will be at bottom. So the in this beam between column C1 and C2, the mean steel will be at the top, and in this cantilever projection, as the tension is at bottom, the mean steel will be at the bottom, okay. This is very important. This is explained over here, right? Okay, fine. So now we know the UDL, okay. So we have to do the analysis of this. It's very simple. I have given this loading to the program MMS software, okay, and I got the corresponding bending moment and shear force diagram, okay. This is the bending moment diagram, this is shear force diagram of the beam, okay, for the given loading, okay. This is the left hand face of the beam, this is the right hand face of the beam, this is the right hand face of the beam, and this is cantilever. Similarly, this is a shear force at the left hand, sorry, this is a shear force at the uh, left end of the beam, this is the shear force at the right end of the beam, this is the shear force for the cantilever, and this is the shear force for this small distance, right? We are taking this is the CG of a column C1, right? And so this distance is 0.25 meters. So this will be the shear force diagram in that area. Okay, so the maximum bending moment is found to be 461.18 kilonewton meter from the analysis, which is at a distance 1.4645, that is from here till here, but the shear force is 0, right? So we know that when the shear force is 0, the bending moment is going to be maximum. So this distance is 1.4645 meters, right? Fine. So now again the first step is we have to check our depth which is provided, okay. So for the maximum moment we have to find the minimum depth required. So minimum effective depth required for the maximum bending moment 461.18, okay, kilonewton meter. Width we have assumed as 600, overall depth we have assumed as 750, okay. And effective cover for beams we are going to assume as 100 mm. Why 100 mm? Let me explain, okay. Let me show you the reinforcement detailing where I can make your mind more clear through showing you the figure, okay. Because the effective cover taken for the cantilever slab footing is 75 mm. So this plus half the diameter of this main steel plus the diameter of the distribution steel plus half the diameter of the beam reinforcement at bottom, right? This will turn out to be 100 mm, right? That is why I have taken effective cover for beam equal to 100 mm, right? That is greater than the slab, that is 75 mm, right? Okay. So as we are taking the effective cover as 100 mm, okay, so the effective depth will be d minus 100, that is 750 minus 100, that is equal to 650 mm, right? So again using the same formula for finding the minimum effective depth d, bending moment is this much, so we get this as 471.91 mm, which is less than 650 which is provided, okay. So it's okay, and the section is under reinforced, so we have passed this check, okay. Now the next step is we have to find the tensile steel for this moment, okay. So and then for the cantilever beam, right? So these sections are very near to each other, so we'll definitely find the steel for both the moments, but we will provide the steel for the maximum moment, right? Okay, so tensile reinforcement required in the beam portion between C1 and C2. Okay, so when the bending moment is 461.18, we the required AST is 2165. We are going to provide 7 number of 20 mm dia bars, which is equal to 2198 mm square, which is greater than 2165. Okay, and the corresponding PT, that's percentage of tensile steel, is 0.5636, right? Okay, the moment near to that, okay, that is 8.88. Okay, so for this the steel required is 2101. We'll provide the same steel as provided over here. Okay, the area is 2198, greater than this, so okay, and the percentage of tensile steel is again 0.5636. So let me show this in the detail so that I can make your mind more clear. We will see the reinforcement detailing. Okay, so reinforcement detailing. Okay, as according to the design moment, we are getting 7 number of 20 mm dia bars, right? But I have written 8 over here. Please don't get confused. This has been written as 8 purposefully because the area of steel which we got from the bending moment criteria was found to be failed when we do the check for the crack width, right? Because the code says the stress in the tensile steel should not be greater than 0.8 F5. Okay, when the steel area was as according to 7 number of 20 mm diabars, then the stress in steel was found to be greater than zero point 0.8 F5. Okay, so I had to increase 1 bar more. Okay, this we will see when we come for when we do the check for the crack width. Okay, but for now, okay, from bending moment criteria we got 7 number of 20 mm diabars, okay, which we will curtail over here, and this we will continue till the support. Okay, because we can see over here, okay, there is a drastic reduction in bending moment. Okay, let me show you the figure. Okay, this distance is just 1.4645, right? So there is a drastic reduction in bending moment. That is why doing curtailment of steel in this area is not possible. Okay, so whatever steel which we get over here, though the moment over here is reduced, but still for satisfying the curtailment criteria, we will have to take all the bars to the columns, to the support, right? That is what we have done over here, right? So let me show you again. Okay, that is why we have continued all the bars into the support, right? Now over here the moment is reduced to 104, I think so. Let me check the bending moment diagram. Okay, over here the moment is 104.39, right? So we can reduce the steel in this area. Okay, so we'll find the steel area for this moment. Okay, the AST required is found to be 455, right? This is less than AST minimum, that is 799. AST minimum is found by this formula. Okay, so AST minimum is found to be 799, and the steel area cannot be less than AST minimum, so we have to at least provide AST minimum. So to satisfy this criteria, we will continue 3 numbers of 20 mm diabars to the support. Okay, and that area is found to be 942, which is greater than 799. So that's okay, right? So let me show you the figure again. Okay, so out of the total bars, only 3 bars we are going to extend till here, right? That is what which is required. So we are doing a curtailment at a distance 1.5 meters from here, right? So other bars are curtailed over here, and only 3 numbers of bars are continued. Okay, and this steel has definitely has to be more than the AST minimum, which we have satisfied. So that's okay, right? Fine. And now let us find the steel required for. Okay, as I explained to you, the main steel for this beam is at top, because in beam the tension is at top. In cantilever the tension is at bottom, so the main steel will be at bottom, right? So that is why we have provided over here the main steel at top, right? So now doing the design for cantilever projection. Okay, and the moment for cantilever projection is 2 to 1.52. We can see the bending moment diagram, 2 to 1.52, right? This is the cantilever. Okay, so for this the steel is found to be 986. We will provide fine number of 16 mm diameter. So the area is 1005, which is greater than 986. So it's okay. And the percentage of tensile steel is 0.2577. Okay. So that is what we have provided. Okay. In the detailing, let me show you the detailing, right? Okay. This is fine number of 16 mm diameters. Okay. Now this is a cantilever, this portion is cantilever. Okay, so these bars have to be anchored properly, and for that anchorage purpose we will continue this bar till the end of the next support. Okay, so we are providing a 5 number of 16 mm dia bar through and through at the bottom, right, with the effective cover 100 mm. Okay, so this is how we do the design of the longitudinal steel. And the anchorage, proper anchorage is a must. Okay, that is LD. Say this is our 20 mm diameter, then the development length that is to be provided should be at least the development length of 20 mm diameter in tension for M25 grade of concrete, right? So that is very important. So development length, you have to give full development length considering the bar is under tension. Okay, fine. So now we will move on to check for shear in case of beam. Okay, so we will see the shear force diagram, and we will design the shear as according to this diagram, right? This is the left of beam where shear force is 648.77, and this is the right hand of the beam where the shear force is 538.57. Okay, so practically we will provide the reinforcement, that is shear reinforcement in this area and this area same. Okay, only we will vary the reinforcement shear reinforcement in the midspan. So we will provide the shear reinforcement for this maximum shear force, that is 648.77. Okay, so let us find, do the shear check for that force. Okay, provide provision of shear reinforcement in the beam between column C1 and C2. Shear force at left hand near column C1 is 648.77, and the corresponding percentage of tensile steel which we have provided at the left hand of the beam, okay, near the column C1. Okay, when you cut that section, then the tensile reinforcement percentage we have provided is 0.5636%, right? So for this corresponding percentage of steel, we have tau c equal to 0.513 Newton per mm square from table 19 IS 456 2000. Now find the nominal shear stress V divided by BD. V is known to us, B is known to us, D is known to us. This is 1.66. This should be less than tau C max. Tau C max is 3.1 Newton per mm square. That is from table 20, okay, of IS 456 2000. So as your nominal shear stress is less than tau C max, so it's okay. Otherwise, you will have to revise your section. But our nominal shear stress is greater than tau C, that is permissible shear stress. So as tau E is greater than tau C, the additional shear stress will be have to taken by stirrups. So VUS is the force that is to be taken by the stirrups, which can be found by this formula, which is equal to 448.7 kilonewton. So this is the formula for finding the spacing of stirrups, vertical stirrups. Please remember, this is the formula for finding the spacing of vertical stirrups. Okay, we are going to use 12 dia 2 leg stirrups. So ASV is the area of two leg stirrups. Okay, so 2 into area of 12 dia, that is 226. Okay, so the spacing is found to be 118.2, right? Okay. Uh, as according to code, the maximum allowable spacing should be list of the following. Okay, this is one formula where ASV is 226. Okay, so this by this we get spacing is 340. By this we get spacing is 487.5, and this is 300 mm, and our spacing is 118.2, which is less than all these three. So we will provide 12 mm two leg stirrups about 115 mm center to center at a distance 0.2 up to a distance 0.25 L from face of the both supports. Okay, we are providing shear reinforcement equally on both the supports for a distance of 0.25 L, that is equal to 1.5 meters. So we will see that we can see 1.5 meters, 1.5 meters. But the stirrups provided in this region is 2 leg 12 mm about 115, 2 leg 12 mm about 115, right? So now we will find this requirement of shear reinforcement in the middle portion of the beam. So in the middle portion of the beam, the shear force is 104 kilonewton. So let us see the shear force diagram. Okay, you can see it is 104.39. Okay, so we will find the shear force, we will find the shear reinforcement for shear force equal to 104.39. Okay, okay, the steel provided at this section is point PT, that is tensile reinforcement. Percentage of tensile reinforcement provided is 0.5636. Okay, so the tau C is equal to 0.513. Okay, and nominal shear stress is 0.267. Okay, nominal shear stress is V divided by BD. So V is this, BD is known to us. This is 0.267, which is less than tau C max and also less than tau C, right? So as tau V is less than tau C, so provide minimum shear reinforcement, right? So you have to satisfy this criteria given in the code. The maximum allowed spacing should be list of the following. Over here we are going to use 8 mm dia 2 leg stirrups. So ASV will be 2 into area of 8 mm dia bar, that is equal to 100.48. So the spacing required is 115.15. 151.15, sorry, 151.15 mm. This is 487.5, this is 300. So the list is 151.15. So we will provide two-legged 8 mm dia stirrups about 150 mm, right? So that is what I have shown in the reinforcement detailing. Okay, so let me show you the ring. So in this middle portion we are providing two-legged 8 mm dia about 150 mm. Okay, center to center. Now coming to the cantilever portion. Okay, in cantilever portion the shear force is 443.04. Okay, so let us see the figure by shear force diagram. Okay, this is the shear force for the cantilever, right, at the face of the support. Okay, so we are taking this and let us, okay, that is what we have taken over here. Okay, so the percentage of steel provided is 2.2577. Okay, so corresponding tau C is 0.372. Tau V is 1.136, which is greater than tau C. So you will have to provide a shear reinforcement. BUS is found to be 298. So vertical stirrups we are going to provide 10 mm dia, 2 leg. Okay, the spacing is found to be 1, 2, 3. The spacing should be less than a list of this, right? Okay, so this is 236, this is 487.5, this is 300. So required is 123 mm, so which is less than this. So we'll provide 2 leg 10 mm dia stirrups about 120 mm center to center. So that is what I have shown in the figure. Okay, 10 mm about 120 mm center to center. Okay, fine. So this is how we did the design of the beam. Okay, that is what longitudinal reinforcement and the shear reinforcement. Okay, fine. Now the next step is we have to do the check for crack width, which is very important. Okay, check for deflection is not necessary because the footing is beneath the soil and which is not visible, so there is no need for doing the check for deflection. And now check for crack width. The crack width should be less than 0.3 mm because our footing lies in a moderate condition. Okay, so we will do the check for crack width for the maximum moment, right? Factor influencing crack width. Okay, the tensile stress in steel bars should not be greater than 0.8 fy as according to the code. Thickness of cover should be less. Diameter and spacing of bars, you should preferably use smaller diameter with less spacing, that is more preferable. That will give that will control your crack width. Okay, depth of member and location of neutral axis, bond strength and tensile strength of concrete, right? So given to us D, the depth of beam is 750 mm, width is 600 mm, effective depth we have taken as 650 mm, Fy is 415, FCK is 25, AST for the maximum moment we have taken is 7 number of 20 mm dia bars, the area is 2198. AC we are taking is equal to 0. Though we are providing a steel in compression zone, there are 5 number of 16 mm dia bars in compression zone, but we are still taking ASC is equal to 0 because we have designed the beam section as under reinforced section. So we are considering the bars in compression zone to be hanger bars. Okay, and assuming that they are not going to take part in design. Okay, so this is elastic modulus of this is for concrete, this is for steel, this is a modular ratio M for a long term, considering long term effect, that is taking the effect of creep, shrinkage and temperature. So for M25 grade concrete, M is 11. Okay, now we have to find the depth of neutral axis. Okay, so for finding the depth of neutral axis, what we do is we take the moment of this area about CG and moment of this area about about the neutral axis, not CG, sorry. This comes from here, area into this distance, that is equal to this, and area into this distance, that is equal to this, right? So solving this quadratic equation, we get xu is 192.103, xu is 192.103. Fine. Once you know xu, you can find mi gross, bdq by 12, mi cracked, that is you have to find the moment of inertia about neutral axis, that is b into x cube by 3, right? Plus mast into square of this distance, right? That is you're going to be that is going to be your mi crack, right? So this is mi gross, this is mi crack. Okay, so as per approximate method specified in IS 456-2000, this is stress in concrete at the level of steel. Okay, please remember, stress in concrete at the level of steel. Okay, so M is the design moment. Okay, D is the effective depth, XU is known, MI correct is known. This is found to be 32.55 Newton per mm square, and the corresponding stress at that level in steel is Fs. So from the principle of transform section, Fs is equal to m into Fc. So 11 into Fc, that is equal to 358, and this should not be greater than 0.8 Fi. 0.8 Fi is 332. Okay, so this is found to be greater than this, right? So which is not okay, and we will have to increase the area of steel, and for that reason I have provided one more added one more 20 mm die bar. Initially it was 7 numbers of 20 mm die bar. Now adding one more, it becomes 8 number of 20 mm die bar. So that area, now your area AST becomes 2512. So that is why I have written over here 8 numbers of 20 mm diabars, because the area of steel which we got from the bending criteria was not adequate to satisfy the crack width criteria. Okay, the stress in steel was found to be greater than 0.85, which is not permissible, so we had to increase the area of steel to bring the stress in the steel less than 0.8 Fy. Okay, fine. So now let us, now as we have increased the area of steel, so we will again have to find the depth of neutral axis. So the new depth of neutral axis is 202.925. New mi cracked, new mi cross is this, new mi cracked is this. So again finding the stress in concrete at the level of steel, which is equal to 28.65. So the stress in steel is m into Fc, that is equal to 315, which is less than 332. So it is okay and safe, right? Okay, fine. Now we have to find strain 1. This is a formula given in the code. Okay, this formula does not include the effect of tension stiffening, right? So everything is known. Fs is known, Es is known, capital D is known, Xu is known, small d is known, Xu is known. This is equal to 0.001928. Okay, now to take the effect, tension effect in account, code has given another empirical method, empirical formula, that is E strain E2. Okay, so this everything is known to us. So this is found to be 0.000266. So mean strain is obtained by reducing this strain from this strain, right? This strain is obtained, is a reduction due to the tension stiffening effect, right? So this is how we get the mean strain, that is equal to 0.001662. Okay, okay. Now as this strain is greater than 0, so our section is cracked. If this was found to be less than 0, then you can say the section is not cracked, definitely. Okay, so now this is the formula for finding the crack width. So for that we have to find ACR. What is ACR? ACR is the distance between the crack and the nearest outer face of the bar. Okay, we we make an assumption that the crack is formed at the mid of the spacing. Okay, this is center to center spacing, that is this spacing, right? And the crack is assumed to form at a distance spacing divided by 2, right? Okay, so how to find this spacing? Simple. We have 8 number of 20 8 number of 20 mm diabars. Okay, this is 50 mm, this is also 50 mm, this is 600 mm. So when you do the calculations, you get center to center distance between the bars as 71.42 mm. Okay, 71.428 mm. Okay, so this is how you get this, right? That is spacing. Effective cover, we know we have taken is 100 mm. Okay, diameter of bar, we know we have taken 20 mm diameter. Okay, so solving this, we get ACR is 96.18. Okay, so putting the value of ACR over here, we get crack width as 0.456, which is greater than 0.3, which is not allowable. Okay, so now what to do? So we can do one thing, that we can reduce the effective cover Okay, so effective cover, instead of 100 we will take 56.5. okay, and solving this again, we get ACR as 56.84, and putting the value of ACR over here, we get the correct width as 0.265, which is less than 0.3, and now the section is safe, right? So that is why initially we had taken this as 100 mm over here, effective core as 100 mm. okay, but that was found to be not adequate. Okay, it was much on the larger side, so we had to reduce the effective cover, and now the final effective cover which you are providing is 56.5 mm, right? So this is how we do the design of the strap footing. Okay, okay, as according to code, uh, when the flexure member does not have torsion, okay, and when the size of the beam, overall depth of the beam is greater than 750 mm, then we have to provide side face reinforcement, right? But to be on safer side, okay, there can be accidental torsions. Okay, so though our depth of the overall depth of the beam is not greater than 750 mm, it is equal to 750 mm, still we will provide 0.1% of the cross section area as our side face reinforcement, right? So we will provide side face bars of area more than 0.1%, okay, that is equal to 450 mm. We will provide 4 number of 12 mm dia bar as side face bars whose area is 452, which is greater than 450. Okay, so we will provide 2 face bar on one side and 2 face bar on other face. Okay, so total face bars are face bar are 4, 2 on each face. Okay, please remember. So I have shown here 2. Another 2 face bar are on the other face. This is one face, and another 2 bars you have to provide on the opposite face, right? So 2 number of 12 mm side face bars on each face placed at equal distance with spacing less than 300 mm. Code says that the spacing, this is spacing 1, spacing 2, spacing 3, right? This should, the face bar has to be equidistant from the top and bottom bars, okay? And and that spacing should not be greater than the least of 300 mm or the width of the beam. Width of beam is 600, and so least is 300 mm. Okay, so the spacing should be less than 300 mm. Definitely our spacing is less than 300 mm, so that is fine and okay, right? Okay, so please visit website mmsprogramcivil.com for all videos and PDF. This video will be uploaded on this website soon. Okay, I hope you must have found this video useful. Thank you.